Hello everyone, this is topic 8 of exam 3, the method of partial fractions. Method of partial fractions is used to integrate rational functions. So we say p of x over q of x where p and q are polynomials. So here's an example of something, just basically a polynomial in the numerator and a polynomial in the denominator. One thing to note is if the degree of the numerator is greater than or equal to the degree of the denominator, then we say the fraction is improper. And one thing you have to make sure of is if you ever see an improper fraction, there's no way that you can integrate until you go through the process of long division of polynomials. So here's an example where long division, I'll do it off to the side. We'll take the denominator, x plus 1, and divided it into the numerator. So x squared plus, okay, if you recall with long division, you need to account for all possible factors or terms that may appear after an x squared. There could be an x. There is no x, so therefore placeholder of 0x, and then plus 1. And then we start the division process. We focus on the first terms. X divides into x squared. Or you can think of what times x gives x squared, and that would be x. Then we multiply, so x squared plus x, 1x if you like. Then we're going to subtract, so our division algorithm, we get minus 1x, bring down the 1, and divide x into negative 1x, we get negative 1, or you can think what times x gives negative 1x, and again that's negative 1. And then multiply, negative 1 times x is negative 1x, negative 1 times 1 is negative 1, and then we're going to subtract, and the x's go away, and we get 1 minus a minus 1, or 2. So here's our remainder, and our remainder goes over the divisor of x plus 1. So this expression is now equivalent to what we had started with. So this is equal to the integral of x minus 1 plus 2 over x plus 1, all with respect to x, and now we can integrate. Let's separate this into 3 integrals just to make the integration clear. So the integral of x with respect to x minus the integral of 1 with respect to x plus, let's factor the 2 out of the numerator there. And the first 2 are readily integrable. X integrates to be x squared over 2. Negative 1x integrates to be negative 1x, or just negative x. And then we have plus 2. And here we're going to encounter this situation quite often because we're dealing with rational functions, so obviously fractions. And our basic formula for integrating fractions is either du over u or u to the n if the denominator is a power. But if the denominator is not a power, then du over u, which results in the natural log of the absolute value of u plus or constant, as we should know. And I'm going to suggest that many of these we just simply do mentally. That is, if you look at this fraction, you can see mentally, without having to make a formal u substitution, that if you choose u to be the denominator, the du is identically 1 dx. So there's really no need for a formal u substitution. We just simply get the natural log of the absolute value of the denominator. So plus 2 natural log absolute value, that denominator, x plus 1. Okay, one good thing that you'll be happy to know is I'm not going to test you on long division, but definitely make sure you understand that it's necessary as you progress through your courses. If you ever see a situation where the fraction is improper, long division must be done first. Okay, so there's 3 basic cases for integrating the method of partial fractions. We have what I refer to as linear factors, that's topic 8, repeated factors, that's topic 9, and then what we call irreducible quadratic factors, which is topic 10. And whatever case we're dealing with, we're going to need to discuss some of the theory behind the concept of what we call decomposition of a function by the method of partial fractions. Now, everything basically stems from the fundamental theorem of algebra, which Gauss had proven way back in 1799. And it says that there's many versions of this, but this is kind of a layman's version. Any polynomial function can be expressed as a product of linear factors and irreducible quadratic factors. So by linear, we mean something like, well, it could be something just like x, for example, or maybe 2x plus 3. Pretty much anything that fits the linear form of mx plus b, ax plus b, whatever you want to write. So that's the idea of linear factors. Irreducible quadratics are quadratic factors that have complex roots. That is, they're not factorable under the real number system. For example, x squared plus x plus 1. If you set that equal to 0, you'd find that the roots are imaginary, so you get complex roots. So it's not factorable. The way we're going to typically see irreducible quadratic factors is going to be as the sum of two squares. So something like maybe x squared plus 25. So that's typically how we see our irreducible quadratics, a sum of two squares, because you know you could factor the difference between two squares, but not the sum of two squares. So in general, anything that's of the form ax squared plus bx plus c, which is not factorable under, let's say, the reals. Okay? So again, typically sum of two squares for us. Alright, so here's a little remark. There's three main concepts that the method of partial fraction relies upon. A rational function can be, here's that term again, decomposed into the sum or difference of two or more simpler rational functions that have either these types of things as their denominators, linears or irreducible quadratics. Another thing to note is the sum or difference of two or more proper fractions is a proper fraction, and that the method of partial fractions is really just reversing combining fractions. So the next two examples will kind of illustrate these things. So not to insult you, but here's a simple algebra problem. Just combine these two fractions. So we'll need a least common denominator, which is going to be the product, in this case, of x plus 3 and x minus 1. And so we'll build up each fraction. So 1 over x plus 3 gets multiplied by whatever's missing from the least common denominator, which in this case is the x minus 1. So multiply numerator and denominator by that. For the next term, plus 3 over x minus 1 gets multiplied by what's missing now is the x plus 3. So multiply numerator and denominator by that. And then we have a least common denominator. It's the product of x plus 3 and x minus 1. Doesn't matter what order. Multiplication's commutative. You could have put a bunch of parentheses up here. The way I wrote it with the multiplication symbol, really not necessary. But if you want to be safe and throw in some parentheses all over the place there, that's fine. Because the 1 and the 3 in particular have to be distributed. So 1 times x is x, 1 times negative 1, negative 1, 3 times x plus 3x, and 3 times 3 plus 3. So that gives us, looks like 4x. 3 times 3 is not 3. 9, of course. So that gives us 4x plus 8 over x plus 3 and x minus 1. So one thing that this example illustrates is that the second comment, remark here, the sum or difference of two or more proper fractions is a proper fraction. So notice that each of these were proper because the degree of the denominator is 1, degree of the numerator. There's really an x up there. You just can't see it. It's really x to the 0. And the degree of the denominator is 1. So these are both proper. And here we have a proper fraction because the degree of the numerator is now 1. Degree of the denominator, if you imagine foiling this out, you get x squared as your first term, obviously. So it illustrates that second remark. And basically, what we're going to do is we're going to reverse the process. That's what the method of partial fractions is all about. We're going to start with something like this and decompose into this. So this will be the decomposition by, I'm just going to say PF, by the method of partial fractions. So again, it's the reverse of combining fractions. So here's a little bit more theory before we get to actual examples. And we're going to decompose and see what the process looks like in terms of decomposition. Okay, I'm starting with the result of our last example. And the first thing we're going to do is, I'll rewrite it. We're going to decide what this decomposition should look like. So it basically is going to come from as many fractions as we have unique factors in the denominator of the original function. So there's going to be 2, one with x plus 3 and one with x minus 1. And let's pretend we don't know where, what these numbers in the numerator are, but we do know for sure that they have to be numbers, because in order to make these, this is a proper fraction, so these two fractions have to be proper. And in order for these two fractions to be proper, I can't put an x up here because then the degrees would be the same. So the only thing I do is put numbers up here. And so we're going to use uppercase letters, we'll say A and B in this situation, respectively, to represent the constants that we're going to solve for. Okay, so now we create, so that's what the decomposition looks like. Now we create what I refer to as the working equation. This is kind of our go-to equation. And we create that by just clearing the fractions. So we're going to multiply by the least common denominator. And I'll just show this once. You should be able to do this mentally. We're basically just multiplying everything by the least common denominator, which is the denominator on the left, the product of x plus 3 and x minus 1. And so on the left-hand side, the x plus 3's and the x minus 1's cancel. So we just get 4x plus 8. And it's equal to a times the x plus 3's cancel. So a times x minus 1. And then plus b times, similarly, the x minus 1's cancel. So b times the quantity x plus 3. So now we have to solve for the constants. And there are actually two ways to solve for the constants. And the two ways, I like to call the first one comparison, and the second one, elimination. So we'll show you both methods, and we'll see one's actually easier than the other. But then when we come back for part 2 of this, we're going to use the easiest one, but we'll then subsequently in other examples, we'll see you might have to use these two methods in combination. So here's the comparison method. The comparison method just basically relies on comparing like terms on either side of the equation. For example, if I want to compare the x's, on the left-hand side there's 4x. On the right-hand side, if we distribute the a, we get that 4x would be ax, and then distribute the b, and we get a bx. And then we could divide out the x's, and we get 4 as a plus b. Now there's one equation, but we have two unknowns. So we're going to continue our comparison, and the only thing left to compare are the real numbers, or the constants. So on the left we have 8, and on the right, if you imagine distributing the a times -1, it would be negative a, and b times positive 3 would be plus 3b. And there's another equation with the same two unknowns. So now we're going to have to solve the system. And you could use any method you like to solve the system of equations. I'm just going to use the standard algebraic method. So if I line up 4 equals a plus b and 8 equals negative a plus 3b, easiest thing to do here in this case is just simply add the two equations together, and the a's are eliminated. But I want to mention something. Okay, there's something I wanted to mention. I grabbed a sheet of paper here. Just make sure you know, like, I'm going off to the side just to illustrate a concept here. Let's say I had 2x plus 3y equals 8, and 3x plus 2y equals, let me make this minus 2y, I'll make it easier, equals negative 5. I'm not going to solve this system, but I just want to point out that using this method, what we do is we take the, we just make the coefficients of one of the variables equal but opposite. So for example, if I multiply the top by 2 and the bottom by 3, then I get 4x plus 6y is 16, and 9x minus 6y is negative 15. And now I can add the two equations together, and the y's are eliminated, and then I can solve for x. So I just wanted to point that out as a general way to approach this. But here this one's easy because we just add them together. We get 12 equals, the a's are gone, 12 is 4b, and b would be 3. Okay, and then we back substitute. And we have, pick either equation. It's just solving a system. It's basically point of intersection. I'll pick the simpler 4 equals a plus b. Replace b. And a is 1. So basically what we've shown, the result, is that we've shown that this 4x plus 8 over the x plus 3, x minus 1, is now equal to, if you go back to the original partial fraction decomposition, a over x plus 3, that was 1 over That would be 1 over x plus 3, and then plus b. B was 3 over x minus 1. So that's using the comparison method. And if you look back at the example that we combined, they were the original constants 1 and 3, respectively, of that of those two fractions. Okay, so comparison method often leads us to a system of equations. By the elimination method, okay, so we're going to separate these. Okay, so now the elimination method. You start exactly the same way. That is, the first two steps, no matter what method you're going to use, are always the same. Here's the original fraction. The decomposition is going to contain two terms, one with x plus 3 in the denominator, another with x minus 1. The only thing that can go above each of those, as we discussed earlier, is a constant term, so a and b respectively. Then we still create the working equation. I'm just going to call this WE from now on. And we're multiplying by this least common denominator. So here, I showed it literally up here in red, but you should be able to do it mentally because you're just multiplying by this denominator right here. So on the left, you're always just going to get the numerator. 4x plus 8, not b. And on the right, if you multiply a over x plus 3 by this denominator, the x plus 3's cancel, get a times x minus 1, and similarly multiply b over x minus 1 by this denominator, the x minus 1's cancel, so we get plus b times x plus 3. So hopefully you're comfortable with that. And then here's the neat thing. What we do is we strategically pick values of x that are going to eliminate all but one of the very constants that we're trying to solve for. And you could just look at this equation and you could say, okay, what can zero this out, right? What can cause this term to be 0? And that obviously is going to be let x equal 1. And then you would say, okay, what about this guy? How can I make him 0? And that would be by choosing x equaling -3. Now, one thing I like to do is to consider, so that's fine, you can go about it that way, looking at the working equation. But I like to look at the original decomposition, because if you look at the denominator of the original decomposition and you force that to be 0, that's going to allow you to solve for the constant that lies above it. So that's what I like to consider. Now, you don't have to do it that way. You could just start picking values of x that are going to zero things out. But here, I always go back to the original decomposition and say, okay, what causes this to be 0? And that's a -3. And then you substitute into the working equation. So 4 times -3 plus 8 equals a times x is -3 minus 1 plus b times. You really shouldn't have to show this substitution because obviously you chose -3, so that term goes to 0. So that's equal to 0. In the future, we won't show that substitution. And then just crunch down the arithmetic, the algebra here. -12 plus 8, -4. 8 times -3 minus 1 is -4. So -4a. And look at that. Immediately, a is 1. And if we let x equal, okay, again, I go up here to the original decomposition, force this denominator to be 0, that'll allow me to solve for b, and by letting x equal 1, that'll work. So then in the working equation, 4 times x is 1, plus 8 equals, okay, last time to show this, again, really no need for that substitution. and then plus b times 1 plus 3. Okay, again, this term equals 0. So we get 4 plus 8 is 12 equals 4b, and b is 3. Okay, so obviously, and so let's just reiterate the result here. And that would be the same as before. So that 4x plus 8 over x plus 3, x minus 1 is the a, 1 over, so going back to the decomposition, x plus 3 plus the b, which is 3, over x minus 1. Okay, so we'll see some examples. We'll come back in a few minutes and have some examples of this. We may need to use, just one final note here, and we'll reiterate this before we start our examples. We might have to use both of these methods in combination, the comparison and the elimination. So we'll see that unfold as we progress through the topics here. So we'll see you when you're ready.